Hello students. In this session, we are going to study about planes. A two-dimensional flat surface is called a plane. Two planes intersect at a line. A plane is uniquely determined if the normal of the plane and its distance from the origin is given. It passes through a point and is perpendicular to a given vector, and it passes through three given non-collinear points. Let us now derive the equation of a plane in normal form. Consider a plane whose perpendicular distance from the origin is d. Let's consider n cap to be the unit normal vector along ON vector. Then ON vector will be equal to d into n cap. Now, let's take a P to be some arbitrary point on the plane with the position vector r. Observe that NP vector is perpendicular to ON vector.
Since the two vectors are perpendicular, their dot product is equal to 0.
So NP vector can be written as OP vector minus ON vector. So substituting OP vector as R vector and ON vector as D into N cap, we get the following step. Distributing the dot product, we get R dot dn cap minus dn cap dot dn cap is equal to 0. Observe that d is the common term. So taking the common term out, we have the next step. We know that n cap dot n cap is equal to 1. Hence, we get d into r vector dot n cap minus d is equal to 0. Now, since the product of two terms is equal to 0, one of the terms has to be equal to 0. Since d is the perpendicular distance from the origin, d cannot be equal to 0, which will imply vector r dot n cap minus d is equal to 0. Therefore, vector r dot n cap is equal to d is the vector form of the equation of the plane. Now, let us derive the Cartesian form. Let us take point P as x, y, z, which will imply vector OP, that is vector R, is xi cap plus yj cap plus zk cap. Let's consider L, M and N to be the direction cosines of n cap. Then n cap will be L into I cap plus M into j cap plus N into k cap. Substituting in the vector form, taking the dot product, we get Lx plus My plus Nz is equal to d as the Cartesian form of the equation. Note that when the plane is perpendicular to n vector, then n cap is given by n vector upon magnitude of n vector. And if P is the perpendicular distance from the origin, then the vector form of the equation, that is vector r dot n cap is equal to d, becomes vector r dot n vector divided by magnitude of n vector is equal to P, which implies vector r dot vector n is equal to P into magnitude of vector n, which will imply vector r dot vector n is equal to d, where d is equal to p into magnitude of vector n. Therefore, the vector equation will be vector r dot ai cap plus bj cap plus ck cap is equal to d, where a, b and c are the direction ratios of the normal vector. To get the Cartesian form, let us substitute vector r as xi cap plus yj cap plus zk cap, and then let's take the dot product. Therefore, ax plus by plus cz is equal to d becomes the Cartesian form of the equation. Now, let us see what happens to the equation of the plane when it passes through a point and is perpendicular to a given vector. Given a vector, we can draw any number of planes which are perpendicular to this vector. But if a point is given to us, we can draw only one plane which passes through the point and is perpendicular to the given vector. We shall now find the equation of this plane. Consider a plane. Let n vector be a perpendicular vector. Let A be the given point with position vector, vector A. Let P be some point on the plane such that its position vector is vector R. Now observe that P lies on this plane only if vector AP is perpendicular to vector N. We can draw this figure like this to make it more clear. Observe that AP vector is perpendicular to the normal vector. Since they are perpendicular to each other, their dot product has to be equal to 0. So we have AP vector dot n vector is equal to 0. AP vector can be written as R vector, that is OP vector, minus OA vector, that is A vector. So substituting, we get vector R minus vector A dot product with n vector is equal to 0. This is the vector equation of the plane. In order to derive the Cartesian form, let us consider point A, the given point, as x1, y1, z1. So the position vector will be x1 I cap plus y1 j cap plus z1 k cap. Let's take the point P, the arbitrary point, as x, y, z. So vector R will be xi cap plus yj cap plus zk cap. Let vector n be equal to ai cap plus bj cap plus ck cap, where a, b, c will be the direction ratios of n vector. Substituting all this in the vector form, we have x minus x1 into I cap plus y minus y1 into j cap plus z minus z1 into k cap dot product with the normal vector, that is ai cap plus bj cap plus ck cap is equal to 0. Taking the dot product, we get a into x minus x1 plus b into y minus y1 plus c into z minus z1 is equal to 0. This is the Cartesian form of the plane. Let us now derive the equation of the plane when it passes through three given non-collinear points. Consider a plane with three non-collinear points R, S and T such that its position vectors are vector A, vector B and vector C. Let point P be an arbitrary point with the position vector, vector R. Let us draw this figure like this to make it little more simple. Observe that vector Rs and vector Rt are both perpendicular to vector Rs cross Rt, because we know that the cross product of two vectors is perpendicular to both the vectors. Hence, vector Rs cross vector Rt forms the normal to the plane. Now, if I draw the vector Rp, it is very clear, since Rs vector cross Rt vector is a perpendicular vector, Rp vector will be perpendicular to Rs vector cross Rt vector. Therefore, their dot product will be equal to 0. We can write Rp vector as OP vector minus OR vector, Rs vector as Os vector minus OR vector, and Rt vector as Ot vector minus OR vector. Substituting OP vector as R vector, OR vector as A vector, OS vector as B vector, and OT vector as C vector, we get the following equation. And this is the vector equation of the plane. In order to find the Cartesian equation, let us write the position vectors A, B, C and R. Let us take the point R as x1, y1, z1. Therefore, the position vector, vector A, will be equal to x1 I cap plus y1 j cap plus z1 k cap. Let's take S as x2, y2, z2. So we have the position vector, vector B like this. Let's take T as x3, y3, z3, and hence we have the position vector of T given by vector C is equal to x3i cap plus y3j cap plus z3k cap. Let's take P, the arbitrary point, as x, y, z. So we have vector R is equal to xi cap plus yj cap plus zk cap. Now, let us find what is vector R minus vector A, vector B minus vector A, and vector C minus vector A. Let us substitute all this in the vector form. Observe that we are taking the scalar triple product. So the first row of the determinant will be components of vector R minus vector A. Second row of the determinant will be components of vector B minus vector A. And third row of the determinant will be components of vector C minus vector A. And this is equal to 0. This is our Cartesian form of the equation. What if we consider three collinear points? Observe that if three points lying on the same line are given to us, then there will be many planes passing through that line. For example, consider your book. Consider 3 points like this. Observe that each page is a plane and we'll get many planes passing through these 3 collinear points. Hence, the planes that we obtain here are not unique. So, in order to get a unique plane, we have to consider 3 non-collinear points. And therefore, we can say, through any 3 collinear points, there is at least one plane, and through any 3 non-collinear points, there will be exactly one plane. Equation of a plane in intercept form. Intercepts are obtained when the line or the plane cuts the axis. Let us consider a plane ax plus by plus cz plus d is equal to 0, which makes intercepts a, b, c on x, y and z axis respectively. Let the planes meet x-axis at P of a, 0, 0, meet the y-axis at Q, and meet the z-axis at R, as given in the figure. Now observe that the point P lies on the plane. Therefore, it should satisfy the equation of the plane. Therefore, substituting a, 0, 0 in the equation of the plane, we get a is equal to minus d by a. Similarly, we get b is equal to minus d by b and c equal to minus d by c. Substituting a, b and c in the equation of the plane, we get x by a plus y by b plus z by c is equal to 1. This is called the intercept form of the plane. Plane passing through the intersection of given planes. Let us consider the plane 1 as pi 1 and pi 2. That the equations of these planes be vector r dot n1 vector is equal to d1 and vector r dot vector n2 is equal to d2 respectively. Let pi 3 be the plane which passes through the intersection of these two planes. The equation of the plane passing through the intersection of plane 1 and plane 2 is given by pi 1 plus lambda times pi 2 is equal to 0. Substituting pi 1 as vector r dot n1 vector minus d1 plus lambda times
plane pi 2 vector r dot n2 vector minus d2 equal to 0, and simplifying we get
vector r dot vector n1 plus lambda times vector r dot vector n2 is equal to d1 plus lambda d2. In order to get the Cartesian form, let us take vector n1 as a1 I cap plus b1 j cap plus c1 k cap, where a1, b1, c1 are direction ratios of n1. Let N2 vector be A2 I cap plus B2 J cap plus C2 K cap, where A2, B2 and C2 are direction ratios of N2 vector. Let R vector be Xi cap plus Yj cap plus Zk cap. Substituting in the vector form, we obtain A1x plus B1y plus C1z plus lambda times A2x plus B2y plus C2z is equal to D1 plus lambda times D2. Rearranging, we get A1x plus B1y plus C1z minus D1, which is the equation of plane 1, plus lambda times A2x plus B2y plus C2z minus D2, which is the equation of plane 2, is equal to 0. Coplanarity of two vectors. Consider a plane with the line 1 given by vector r is equal to vector a1 plus lambda times vector b1, where a1 vector is the position vector of point A on L1 and b1 vector is a vector which is parallel to L1. Let us consider L2 as vector r is equal to a2 vector plus lambda times b2 vector, where a2 vector is the position vector of point B on L2 and b2 vector is a parallel vector to L2. AB vector will be OB vector minus OA vector, which is equal to A2 vector minus A1 vector. Now observe that vector b1 cross b2 vector will be perpendicular to the entire plane. Hence, it is also perpendicular to vector AB because vector AB lies on the plane. Since they are perpendicular, their dot product will be equal to 0. AB vector can be given as A2 vector minus A1 vector. So substituting, we get A2 vector minus A1 vector dot B1 vector cross B2 vector is equal to 0. This is the vector equation. In order to get the Cartesian equation, let us consider vector A as x1 I cap plus y1 j cap plus z1 k cap, a2 vector as x2 I cap plus y2 j cap plus z2 k cap. Vector a2 minus a1 will be x2 minus x1 into I cap, y2 minus y1 into j cap plus z2 minus z1 into k cap. Let us take vector b1 as a1 I cap plus b1 j cap plus c1 k cap and vector b2 as a2 I cap plus b2 j cap plus c2 k cap. Substituting in the vector form, observe that it is the scalar triple product, so the determinant will have its first row as the components of A2 vector minus A1 vector, second row will be the components of the B1 vector, and the third row will have the components of the B2 vector. And hence, we have the Cartesian form given like this. Angle between two planes. Observe that the angle between two planes, plane 1 and plane 2, will be the angle between their normals. So let us consider n1 vector to be the normal of plane 1 and n2 vector be the normal of plane 2 as given in the figure. We have angle between two planes is equal to angle between their normals, which is given by cos theta is equal to modulus of n1 vector dot n2 vector divided by magnitude of n1 vector into magnitude of n2 vector. In order to derive the Cartesian form, let us consider the equation of plane 1 as a1x plus b1y plus c1z plus d1 is equal to 0. From this equation, it is clear that a1, b1 and c1 are the direction ratios of the normal to the plane 1. Therefore, n1 vector will be equal to a1 I cap plus b1 j cap plus c1 k cap. Similarly, let plane 2 be equal to a2x plus b2y plus c2z is equal plus d2 is equal to 0. Here, a2, b2 and c2 are the direction ratios of the normal to the plane 2, that is the vector n2. Therefore, vector n2 is equal to a2i cap plus b2j cap plus c2k cap. Substituting this in the vector equation, and for the numerator, we have to find the dot product of n1 vector and n2 vector, that will be equal to a1 into a2 plus b1 into b2 plus c1 into c2, divided by magnitude of n1 vector will be square root of a1 square plus b1 square plus c1 square, and magnitude of n2 vector will be equal to square root of a2 square plus b2 square plus c2 square. Now what happens if the planes, plane 1 and plane 2 are perpendicular to each other? Then theta is equal to 90 degree. In other words, the dot product between their normals will be equal to 0. And also, if the planes are parallel to each other, then the direction ratios of the normals will be proportional. Distance of a point from a plane. Consider a plane P1 with the equation vector r dot vector n is equal to d. Dividing this equation on both the sides by magnitude of vector n, we obtain vector r dot n cap is equal to d by magnitude of vector n, which is the equation of the plane in normal form. This equation will imply that the distance of the plane from the origin is d by magnitude of vector n. Let us consider a point. We have to find the distance of the plane from the point. How do we do that? Let us consider a plane which passes through this point and is perpendicular to the given vector, that is vector ON. Let vector ON meet the plane 2 at n dash. Observe that plane 2 is the plane which passes through the given point and is perpendicular to the vector ON dash. Therefore, the equation of plane 2 will be equal to vector r minus vector a dot vector n is equal to 0. Simplifying this, we get vector r dot vector n is equal to vector a dot vector n. Let us divide this by magnitude of vector n. We obtain vector r dot n cap is equal to vector a dot n vector divided by magnitude of n vector, which is the equation of the plane in normal form. Now this equation will imply that the distance of the plane 2 from the origin is vector a dot n vector divided by magnitude of n vector. We have to find the distance between A and the plane 1, which is same as the distance between plane 1 and plane 2. So we have to find the value of n dash. n dash is equal to on minus on dash from the figure. Hence we obtain n dash, that is distance of a point from a plane or distance between these two planes, equal to modulus of d minus a vector dot n vector divided by magnitude of n vector. We are taking modulus because distance is a positive quantity. Since we are taking the modulus, we can write modulus of d minus vector a dot vector n also as vector a dot vector n minus d. Let us take vector a as x1i cap plus y1j cap plus z1k cap and vector n as ai cap plus bj cap plus ck cap. Substituting in the vector form, we get modulus of ax1 plus by1 plus cz1 minus d divided by magnitude of vector n, which is a square root of a square plus b square plus c square. This is the Cartesian form of the equation. Let us now find out the angle between the line and the plane. The angle between the line and the plane is the complement of the angle between the line and the normal to the plane. Let us consider the equation of the line as vector r is equal to vector a plus lambda times vector b. where vector b is a vector which is parallel to the line. Let the equation of the plane be vector r dot vector n is equal to d. Let theta be the angle between the line and the normal. So theta is the angle between vector b and vector n. So 90 degree minus theta will be the angle between the plane and the line. Therefore, we have sine 90 minus theta, which is equal to cos theta, is equal to modulus of b vector dot n vector divided by magnitude of b vector into magnitude of n vector.